for different materials, first of all. So metal constant temperature, we've done this experiment. Okay, so constant temperature, voltage is proportional to current. We get a straight line graph through the origin. Ohm's law is obeyed. That's fine. Okay, you have to know what the charge carriers are. So in a metal, charge carriers are electrons. Filament bulb, it's just a metal, right? So we're going to put in here metal not at constant temperature. That's what it is. Okay, so the charge carriers, you have to know electrons. And you get this. Now, we know that. So let's go through why we get this. We're going to put it over here to the side. Okay, so as V increases, I increases. Okay, now if you think about it, from Joule's law, as I increases, delta theta increases. We're going to write in here Joule's law. Now if delta theta is temperature, and as temperature increases, resistance increases. So as V increases, I increases. As I increases, delta theta increases. As delta theta increases, which is a change in temperature, resistance increases from that form of experiment. So therefore, current is less than it should be. Now, it's well worth being able to go down through all of those because it uses about 3 or 4 different experiments. Okay, so I against V, right? And so effectively, look, the current, as voltage increases, the current should increase and should be linear. But as the temperature gets higher, as the voltage gets higher and the current gets higher and the temperature gets higher, the resistance gets higher. So instead of having a current of this, you're getting less of a current because the resistance is too large. That's worth thinking about. Okay. Active electrodes and inert electrodes, well, we're not worried about these. Okay, don't worry about these for the present. Okay, that does obey Ohm's law. This doesn't, even though it is linear. Okay, and we will come back to that, but ignore for the time being. Also ignore this for the time being. Okay, but we're just going to draw it for the time being. Okay, and we will come back to it. Okay, but not relevant. And this is not relevant to what we're doing. So what we're interested in really is the first, effectively the first 3. Okay, ignore the rest. Okay. And we've just looked in the calculation, if you go on to page 14, in our introduction, the idea of power in a circuit, okay, or power in the transfer of heat, transfer of energy and minimizing heat losses, apologies, okay. So this is our formula for minimizing, for heat loss. So if we want to minimize heat loss, we want I as small as possible because the heat lost per second, which is the power lost, is proportional to I squared. So the smaller the current, the less power we lost. Power transmission has to be calculated using this, as we've just seen. So if we want to keep E constant and we want I small, well, V must be large. The power transmission is constant, since if P is equal to VI, the smaller I, the larger will be V. So these are the 4 points. That's why we use large voltage, low current devices. Finally, bonding. Okay, domestic circuits, just to run through again. Bonding. So any metal piece, same with earthing, anything that's metal connected to earth, so that if they go live, current will flow quickly to earth and blow the fuse. Fuses are miniature circuit breakers. In both cases, same idea. If current goes above a certain value, it turns off the circuit. Okay, for a miniature circuit breaker, we can fix it. For a fuse, you must replace the fuse. And the RCT is different. Current in should be current equal to current out. If the current in is more than the current out, something has gone wrong and you break the circuit. Okay, different to MCB, and that's important. Real and radial circuits, we're going to ignore kilowatt hour. Just have a look at that, pretty straightforward. That's it. Thanks again.